Hi students, in this chapter we are going to learn about fluids and mostly liquids that we see all around us. We are going to learn how bodies float, we are going to learn what happens to a fluid when it is accelerated, and we are even going to learn interesting things like how we can use the power of fluids to lift something, as massive as a huge truck. We will learn about all this and more in fluid mechanics. So first of all, let us try to understand what a fluid really is. A fluid is a substance that continually deforms when a force is applied tangential to its surface, no matter how small this tangential force is. What does this mean? You see, if you take a solid like this, and if you apply a force tangential to its surface, something like this, what will happen? The solid will get deformed, isn't it? It will offer some resistance to the force you apply, isn't it? See, if you apply a force on the top of this block towards the right, the block will tend to stop your force, isn't it? It will resist your pull. Or if you apply a very large force, the block will break, isn't it? Something like this. On the other hand, a fluid is a substance that cannot withstand any force tangential to its surface, no matter how small that force is. So in this case, you saw that the solid first resisted the force, isn't it? So a fluid does not resist tangential force. It cannot withstand tangential force only. So whenever a force is applied tangential to a fluid, it changes its shape so that the force becomes normal to the fluid. Understood? In general, fluids are liquids and gases. So, you cannot apply a force that is tangential to the surface of the water. Understood? If you apply a force that's tangential to the surface of the water will change its shape. This is the definition of a fluid. A gas or a liquid, that is. Let us now, move on further and understand many aspects of fluid mechanics, the science of fluids. In due time, we will also try to apply forces on fluids. Then you will understand better why fluids can withstand only tangential forces. The first concept we need to study is the pressure inside a fluid. Now, why must there be any pressure inside a fluid? Like, if you look at this point inside a fluid, why should there be pressure here? The pressure inside the fluid is because of its molecules colliding with their surroundings. If you consider a plate A like this, inside a fluid, in that case, the molecules of the fluid apply a force on it from the left side and from the right side, isn't it? The pressure being applied on this plate of area A is the net force on the left divided by A. Understood? Force upon area. Similarly, the pressure from the right is force upon area. So the pressure at any point in a fluid is because of the molecules colliding with their surroundings. So if you take any surface area like this, molecules from the left collide with this surface, molecules from the right collide with this surface, and that is why there is pressure inside a fluid. Understood? And what is the value of the pressure inside this fluid? It has been found by scientists that the pressure inside a fluid is constant in the horizontal direction if the fluid has a constant density. So for example, liquids like water, oil, mercury, all of them have constant pressure in the horizontal direction. This has been found by scientists. On the other hand, in the vertical direction, pressure varies. Let's look at the pressure variation inside a fluid in the vertical direction. We've taken this blue fluid here, and we've taken a very tiny element, that is a small cuboidal element inside this fluid, here towards the bottom. Now let us try to calculate the net fluid pressure in the vertical direction about this block. This elemental block is a distance y below the surface. Its width is dy. The liquid is at rest. What will be the pressure at this distance y from the surface of the liquid? That is what we want to calculate. To calculate that, let us balance the net force on this cuboidal element in the vertical direction. In the vertical direction, a pressure P is present at a depth y from the surface. So the net force in the vertical direction on this small element is P into A, where A is the topmost surface area of this element. The net force in the vertical direction upwards from the bottom is P plus dP into A. Now, as the width of the element is dy, as we move downwards, the pressure increases by dP as we move downwards by depth dy, isn't it? Of course, the weight of the element, dm into g, where dm is the mass of the element, also acts downwards. The element is at rest as the liquid is at rest. Balancing all these forces, we have Pa minus P plus dP into A plus dm into g equal to 0. The mass of the element is density of the liquid into surface area of one side of this element into width of the element, isn't it? Rho A dy. Dm is rho A dy, where rho is the density of the liquid. When we simplify this expression, dP by dy comes out to be rho g. Understood? This means that the pressure variation, as we go down inside the liquid with depth y, is such that dP by dy is rho g. So when we take dy to the other side and integrate on both sides with limits from P0 to P for pressure and limits from 0 to y for the depth below the surface of the liquid, we get this expression for the pressure at a distance y below the surface of the liquid. P equal to P0 plus rho gy. Understood? So you must remember this expression. The pressure at a depth y below the surface of the liquid for any liquid at rest and of constant density is P equal to P0 plus rho gy. Here P0 represents the pressure of the liquid on the surface. Understood? It's the pressure of the surface of the liquid. Now at the surface of the liquid, the pressure of the liquid is the same as the atmospheric pressure because the surface of the liquid is exposed to the atmosphere, isn't it? So P0 is generally taken to be atmospheric pressure also. Note that in this expression, we have taken rho to be constant. Rho is the density of the liquid. Understood? If rho was not constant, when we integrated on both sides by taking dy towards the right side, then we couldn't, directly integrate dy. We would have to take into account the variation of density with y also. Understood? So this is the expression you must remember. Let's solve a problem now to understand this concept better. What is the pressure at points 1, 2 and 3 and 4? The atmospheric pressure is 10 raised to 5 pascals and the density of water is 1000 kg per meter cube. What is the pressure at points 1, 2, 3 and 4 if water is replaced with a liquid whose density varies as 1000 plus y kg per meter cube, where y is in meters? So this diagram is given in the question. We have to find the pressure at 1, 2, 3 and 4 if the liquid given is water in the first case and in the second case it is a liquid whose density varies as 1000 plus y kg per meter cube. So what do?